Hello, lovely Science 9. This is our last lesson for the year, our last lesson for the whole year. And then you get to go out and just be in the sunshine and enjoy your summer. And hopefully, the fall will have some sort of structure and order to it that makes more sense than this did. But anyway, today we're going to be looking at circuits. And God, I hope you watch this because it literally took me hours and hours and hours to put this together today. But that's okay. So we are going to be looking at simple circuits. We will be looking at what it means to have an open circuit or a complete circuit, a closed circuit or an incomplete circuit. Those are synonyms. We'll be looking at series circuits, we will be looking at parallel circuits, and we won't be looking at short circuits because I forgot to do this and it's already almost, well, it's 1 o'clock and I need to get this out to you guys, and besides which you won't care because you'll forget it all anyway. But that's all right. We're just going to go on and do a few things so that you won't look like an idiot if you take Physics 11. Okay? So, a circuit, I think you already knew this, it is a path that the electric current travels on. Okay, so you need to have a conducting path. Can't just be any old path. If you have an insulator, you are out of luck. Okay, and a simple circuit has three components, that are necessary to have a functioning electric circuit. And those are, number one, a source of voltage. So you can either plug it into the wall, an electrical outlet, or you can have a battery. Those will provide the potential energy, okay, provide the potential energy for the electrons. They will allow them, they will bring them to the top of the hill so that they can flow down the hill to their low potential energy state. And in that process, they can give that energy to another device, and that device can do some work. Well, in order to go through that device, they need a conductive path. Okay, that's usually going to be a wire, but if we, I think we did this in class. Um, we had this light bulb apparatus and there were a couple of wires and we dipped it into a solution and the light bulb lit up. Okay, you could have a conductive solution, in a beaker, you got some water, and as long as you got like dissolved ions in there, you might have Na plus ions and Cl minus ions, it can conduct. Don't worry about that. Wait till grade 12. That'll be exciting. And finally, you need a load, which is something that uses up the electrical energy. So this is going to be a resistor or a light bulb. If you don't have a resistor or a light bulb, if you just attach one end of a battery to another, oh look, I am going to talk about it, you will have a short circuit. And the problem with the short circuit is that there is nothing slowing the electrons down. So they're going to move super fast and they're going to cause everything to heat up, and you'll maybe cause a fire, or you'll certainly injure yourself. Your battery will be dead. Life will just suck. Okay? So you need to have something providing the energy, something using up the energy, and something through which the electrons can flow. So here is our simplest circuit possible. All right, we have a battery. This is our source of voltage. And at the negative terminal, remember we have lots of electrons built up at this terminal. The chemical reactions have moved them there. And so the electrons are going to flow away from that excess negative charge. They're going to flow up through. Now this is interesting. Watch how this light bulb works. The electrons flow through here, and then they go through the little wire, la 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 la, and then they go back down here, and they actually come out the side. There's a wire that comes out the side. So there's an attachment at the bottom, and then there's an attachment on the side of the light bulb. And the electrons flow up, and then they flow across, and then they flow down, and they go back over here where we have an excess. The protons, their electrons have left them and flowed to the other side. So there's an excess positive charge here, so the electrons are going to flow that way. Okay, so we have a counterclockwise flow of electrons here. Whoops, that would be, oh my gosh, that's terrible. Let's try that again. Counterclockwise flow of electrons, electron flow. All right, and we could simplify this circuit a little bit, okay? Now, you'll notice what I've done is I've taken the battery, which was like this. You know, we got our positive terminal here and our negative terminal here. And I've just turned it on its side. Okay, so I now have my positive terminal over here and my negative terminal over there. But all I've done is I've just turned it on its side. Okay, this is exactly the same circuit as before. We've just left out some of the details. So the electrons are going to flow from the negative terminal around this complete simple circuit, up through the light bulb, la 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 la, out through the side of the light bulb, la 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 la, and down and all the way around. Okay? Now, if you're anything like me, I could not draw these on my own, hence the many hours spent finding decent diagrams that I did this morning. I can draw a decent schematic diagram though. Okay, a schematic diagram, scheme, from the word scheme, schematic. We're using symbols to represent things, okay? So we have some symbols and we have some choices, okay? So the symbols that we can do so far is we're going to have a light bulb, and you can either draw a light bulb as a circle with an X in it, or you can draw it as this little squiggly do here, or you can draw it as a single whoop up and over, or you can draw it as a whoo, a single loop. So you can kind of do like a double loop-de-loop, or you can do a bump, or you can do a single loop-de-loop, or you can do an X. I like the X because it's easy to draw, okay? You can choose whichever one you want to, okay? Just be aware that probably in my answer keys, a lot of them are going to have the X because, like I said, it's easy to draw. Now, a cell is just a battery, okay? And we draw it in our diagram by drawing a long line, which is the positive, and a short line, which is the negative. And I always like to think that positive numbers are bigger than negative numbers, and so the positive line is bigger than the negative line. You can label the two terminals as being positive and negative, or you can just not label them, and you can assume that your other physicist reading this diagram will know that this is the positive terminal and this is the negative terminal without you labeling them. The other way I think about it is that if I was to take the positive, it's made out of two lines. Okay, so I have a line and I have another line, and if I put them together, it makes a big long line, right? I've got a line and a line. I turn one on its side and it makes a big long line. Oh, look, the long line is the positive. And then the little line is just like a little negative sign, okay? I don't know if that helps, but it helped me. Anyway. Okay, so we were going to draw a schematic diagram, and one of the things that you need to realize is that you need to make your diagram as rectangular as possible, okay? So no jiggity jogs, no wibbly wobblies, just square and boring, okay? So we have already taken this picture here, okay, and we have transformed it into this picture here. However, this still involves more drawing than I would like, so we're going to use our schematic diagram to draw this. And in order to do that, what we're going to do, I'm going to keep that in sight so you can keep an eye on this one, okay? We are going to draw it like this. We are going to draw a cell. Now we have our negative terminal on the left, and we have our positive terminal on the right. And remember, the negative terminal is the small one. So I'm going to put the small one here, and I'm going to put the big one, which is the positive terminal, on the right. Notice I'm making my corners square. Now, down at the bottom, I'm going to put a light bulb. And I could put the fancy wibbly-loo light bulb, or instead of drawing it like that, I could still have my cell. Would it matter if I put my light bulb over here? Does that make any difference whatsoever? Well, the truth is no, it doesn't. You still have this wire attaching the positive end to the light bulb, and you still have a wire attaching the positive end to the light bulb, and we've just drawn it a little bit thicker here, or longer rather, Okay, and then we have this portion of this wire that attaches the light bulb to the negative terminal, and we have this that attaches to the negative terminal. So really, as long as I've put things in a reasonable order, it doesn't matter whether I put them on the top, the side, the bottom, whatever. Okay? All right, what else could we do? Okay, so here you'll notice I have my original diagram. And if I wanted to, in the past couple diagrams, I put the cell at the top. The cell doesn't have to go at the top. The cell could go on the side. I could put my cell here. Okay, I've got my positive terminal on the top and my negative terminal at the bottom. So the long line on the top and the short line on the bottom. And I'm going to make it a square, and I could put my light bulb. Why don't I put my light bulb here this time? Why don't I make it this kind of light bulb? Sure. What the heck? Can I do that? Yes, I can. Oh my gosh. What if I did something wild and crazy like this? Okay, there's my positive terminal, and it's attached to a light bulb. Oh, and then what if I did like that? Is that okay? Yeah, absolutely. It's totally okay. Because look, I still have this positive terminal attaching to the light bulb here, right? Positive terminal attaches by a wire to the light bulb. And then I have the other part of the wire that it brings the light bulb and attaches it back to the negative end. Wow. Okay, and the length of the wire does not matter. So I can put them anywhere I want to as long as they are in the correct order. Okay, next we're going to talk about an open circuit. Okay, and an open circuit is also known as an incomplete circuit. And this is where the electricity cannot flow because there is no complete connection. Look at that. Uh-oh. There's a gap. There's an air gap. Air has no free electrons. So it's a terrible conductor. Air has no free electrons. Not only that, the particles are really far apart from one another. Like the atoms, the molecules, particles are really far apart. So it is a totally good insulator. It is a terrible conductor. Okay? So the air gap is an insulator. Its resistivity is very, very high. Ooh, look at that. We brought in last week's stuff. So this is an incomplete circuit, and you'll notice the bulb is off. However, if we have a complete circuit, also known as a closed circuit, oh, I suppose I should label this one over here as an open circuit. Why is it open? Because there is this open gap. Okay? Why is this closed? Because the gap has been closed. All right. And if we look at this, we see, oh, look, now the light bulb is lighting up. We have it shining, and we have a complete circuit or a closed circuit. We have closed that gap. All right. Now, we could add a switch. Let's get this the right size. There we go. We can add a switch to a simple circuit. And this particular kind of switch here is called a knife switch. Knife switch. And you can either lift it up or you can bring it down. Right now it's in the down position. This is made of metal. So when it is down like this is also metal and metal, you have a complete circuit. Yes? Because this metal touches this metal and the electrons can flow. Now, which way would the electrons flow? Let's see. Electrons flow from negative to positive. So the electrons would flow this way. They would flow in a counterclockwise direction. That would be our electrons flowing. Okay. Let's open that switch, okay, you notice we've opened it. Now there's no connection between the metal and the metal. And so now we have an air gap there, so this is an open circuit or an incomplete circuit, and the light is off. Okay. Now, oh, what do I have over here? I don't think those were supposed to be there, but that's okay. Okay. Here are a bunch of symbols. Let's just remember we have our various symbols for the light bulb. Okay, we have our various symbols for the cell, and now we are going to introduce the symbol for a switch. There are a couple ways of doing it. You can show it like this with the little open circles, la 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 la, like that. And then you can close it, and when it's closed, you can kind of be like, oh, it's resting on top of that. That to me seems like a lot of work. That's hard to draw. So I have a tendency to use this one here, because if I want to draw it closed, I can just go, oh, look, there's a closed switch. And if I want to draw it open, I just go, oh, can't do that. I just go, oh, it's open. Okay, and in fact, this little dot here, sometimes you won't even see that. I like to draw it just because I'm like, oh, then I can see like later on it's closed, but there we are. Okay, and we are going to use those symbols. Okay, now we're going to draw this circuit, and you'll notice that we have the sticky uppy end of the battery is over here, so that is the positive terminal, and on the bottom would be the negative terminal. So we're going to draw our battery like this. Now, when you draw your circuit diagram, I do not want to see this. Wah, la 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 la. Oh, what happened there? There we go. Oh, something weird. Anyway, I'll have to fix that later. And then I would have my little diagram, and then oh, and then I got a switch. Okay, no, 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 no. This would be very unhappy. Okay, that would not be a happy diagram because it is not square. Okay. Now, I'm going to use these as a basis here. What we can do then is we can say, okay, I'm going to put my light bulb here. Okay, there's my light bulb. And it is attached to the positive terminal of the battery. There's my positive terminal of the battery. There's my negative terminal. And the negative terminal is attached to the switch. And look, it looks like a square. Okay, and this is now open. All right, so that's open. So that light bulb will be off. Here are a couple other ways we could draw those circuits. Okay, we could draw them like, oh, here we've got a closed one. We could draw it like this. We could say, okay, here's my positive and negative terminal of my battery. I could draw the light bulb over here, and I could draw my switch. Oh, I could draw it in that same line if I wanted to. I could put that here, or I could put it here. It really doesn't matter. Okay, there we go. And then this one is, oop, that one is wrong because that is a closed circuit. You'll notice the little light bulb is lighting up. Whoa! Okay, and it is closed. This one over here is open. You'll notice the light bulb is dim, and we could draw that. Oh, you know what would be fun? I'm going to put my positive terminal here and my negative terminal here. And I'm going to put, oh, could I put my light bulb at the top? Sure, because my light bulb is attached to the positive terminal. Yeah? My light bulb is attached to the positive terminal. So I could put my light bulb up top if I wanted to. It doesn't matter. And I could, if I wanted to, do it like this kind. Okay, just for something different. And then could I put my switch over here? Sure, I could. Why not? Or I could even put my switch down at the bottom, but I'm going to put it here. I'm going to say it's open, and there we go. Okay, there's innumerable different ways you could draw this as long as you've made it a square, and as long as the positive terminal of the battery is connected to the light bulb. and the negative terminal of the battery is connected to the switch, you are good to go. Okay? All right. If a circuit contains more than one load, ooh, more than one, and remember a load is a thing that uses up electrical energy, a thing that uses up electrical energy. It will be one of two types of circuits, depending on how the loads are connected. In a series circuit, there is only one pathway, let's follow it, whee, through which the electrons can flow. Now, if we have a parallel circuit, the electrons can either flow, oh, and I should draw them coming from the negative, they could go this way and back here, or they could go, and watch this, this is interesting, right? They could go this way. Oh, and instead of going through that light bulb, they go through this light bulb. Okay, and notice that some of the electrons go through bulb A, the ones that are colored yellow, and some of the electrons go through bulb B, the ones that are colored blue. Okay, so some electrons follow the yellow brick road, follow the yellow path, follow the yellow brick road, and some of them follow the blue path, which actually means that you're going to have more electrons flowing in the area where you have both yellow and blue than in an area where you only have yellow or an area where you only have blue. We're not going to get into that this year, which makes me really sad, but that's okay. All right, now if we have a bulb broken in a series circuit, and I'm going to go zoom right in here so you can see, can you see that not only is our bulb broken, but that little filament is broken? Okay, we have a broken filament. Okay, and when that is broken, what it means is that the electrons would like to be flowing. Can I draw my red line on there? Okay, but they don't have a complete path. Here is a path. Okay, it goes up and down and through here, and then out, up and down, and then goes up here and oh no! I now have an open or incomplete circuit. And what that means is that the electrons cannot flow, right? They'd like to, but they can't. And they can't flow through this bulb either because they get stuck when they get to here. And it's kind of like, you know, if you had bumper to bumper traffic all the way around this circuit, and there was like, I don't know, you know, the bridge was down and you couldn't go around the circle. Well, everyone would just be bumper to bumper and no one would move anywhere because there's like a bridge that you can't cross because the bridge is broken or something. Okay? So, if one bulb breaks in a series circuit, the circuit will be open or incomplete. Incomplete. And so the light bulb, the unbroken light bulb, will not work. It won't glow. If we have a parallel circuit, however, okay, and we have one branch of the circuit, all right, so remember, we had, what was the first one? This was the yellow branch, okay. La, 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 la. Oh, and you know what? That yellow branch is broken. The yellow branch of the circuit is open. It's broken. Okay, so it cannot, the current cannot go through there. So all of the electrons, in this case, all of the electrons are going to go, even the yellow ones say, hey, I can't move that way. So I'm going to go through here and I can't go through that pathway, so I'm not going to bother with it. And the blue ones that we had before are also just going to go through here. So actually, this second bulb is going to be brighter than it was before because it's got more electrons passing through it. But this second light bulb can continue to glow because we have a complete path. One of the pathways is broken, but the other pathway is not broken. Okay, so this will be an open, but the other will be closed or complete. Complete. So the unbroken light bulb will work. Woo, how exciting. Okay, so all our symbols again, they're just here. I keep drawing them because, you know, the more you see them, the better. Light bulb, the X, the loop-de-loop, the bump, and the single loop. The cell, you can either label the positive or just have a longer line for the positive. Okay, and the switch. So I would say out of all these choices, if it were me, I would probably use this one. Light bulbs, you pick which one you like. I'm good with all of them. The cell, if it were me, I'd pick this one because it's the simplest. Yeah, but if you like labeling positive and negative, feel free. You can go ahead and you can label positive and negative. For the switch, I like this one. You can choose to do the other one. It just involves a little bit more talent in your drawing. Now there's a few other things here. There's a fuse. Now, inside this fuse, you can see this melty wire. Why is it called a melty wire? Because that's what I call it. It melts at a fairly low temperature. So if there is too much current flowing at any one time and it starts to get too hot, this melty wire is going to melt. Okay? It's not melty to start with. It only melts at a higher temperature. Okay? At normal temperatures, it will just be fine. And once it melts, there will be a gap in that fuse, and that will stop the circuit from it'll open the circuit at that point, and it'll stop things from flowing. So if the current is too great, you want a fuse there or something similar to turn off the electricity so that you won't end up with a fire. Okay, so this opens the circuit. It makes it incomplete rather than allowing it to go with a too high current and causing a fire. Okay, two symbols for a fuse. You have this wibbly woo one, or you have this one. I'm going to say go with this one because guess what? It's simpler to draw. It's just a little box. I don't think I actually put any motors in, so we can just skip over the motors. If you want to draw a motor, that's what it looks like. It's an M in a circle. I would use this one. Now resistors, you looked at those last week. This is what they really look like. Okay, and you can either draw it as a 1 peak, 2 peak, 3 peak, or you can draw it as a 1 peak, 2 peak, 3 peak, 4 peak, or you can draw it as a like this. I'm really going to recommend, you know me, I'm for the simple. I love the simple. I am going to say, though, in North America, this is the one we use. If you were in Europe, you could use the rectangle-y one. But we just don't in North America. This one is the one we use. And I like this one because it looks like a series of speed bumps. And if you think about a circuit like traffic, like a traffic circle, and if you've got speed bumps on that circle, that's going to slow the flow of traffic, and that resistor is going to slow the flow of electrons. Okay, and then last but not least, just because it's fun, I thought I would throw in an LED, a light emitting diode. It's one of these things, you can find them all over the place, and it's got like kind of a confusing little symbol, so I mean, don't worry about it if you don't get this. You can either draw the triangle blank, which is easier, or you can fill it in. Okay, and then you can show light coming off of it. That's how they do it. I don't like that one because it's complicated regardless, but I think there's only one in this whole thing, so there we go. So from the above choices, draw the schematic symbol that we have chosen. Okay, so you're going to go back here and you're going to be like, okay, I choose this one and this one and this one, and this fuse, and this motor, and this resistor, and I'm going to draw them all down here. So for example, I might draw 1, 2, 3, and label that resistor. Why am I having you do that when they're right there? Because if you write it down, you will remember it. So do all of them. There should be, how many should there be? Let's take a look. There should be 1, 2, 3, 3, 4, if you include the open and close switch. 1, 2, 3, 4, 5, 6, 7, 8. Okay? 8. So there should be 8 things that you draw there. Oh, and one extra thing. We can actually connect cells in series. So if I had a battery, okay, we call it a cell, okay, and there's my positive terminal, and there's my negative terminal. I can actually link it up end to end with another battery, okay, and maybe actually what I'll do is I'll go like this. Gosh, I cannot draw. It's really sad, but that's okay. I don't care. So there's our positive, negative, and there's our positive, negative, there's our negative, positive. And if I was to do that, I would have two cells in series, and I would draw it like that, just end to end. In fact, I can still draw it like that, even if I stick a wire between them. It's no big deal. Okay, so even if I had like this, my positive and my negative, and I drew a wire in between them, helps me to draw if I sing. Okay, so even if I did it like that, I could still draw it just like this. No, oh, except for I would draw negative, positive, negative, positive. This one would actually be backwards. I should have drawn this one like negative, positive, negative, positive. And if I had 4 batteries all in a row, I would draw it like that. I just make sure I put my negatives and positives on the correct side for how the picture is drawn. Okie dokie. So let's practice a few of these before I send you off on your own. So what I would often see a student doing if they hadn't, been through the whole make it square is they would draw like, okay, I've got a cell and I've got my, let's just pretend this is positive and negative, positive, negative, positive, negative. Okay, and they'd be like positive, negative, positive, negative, positive, negative, and then we draw a switch, and then they draw a light bulb, and then they draw a light bulb, and then they'd be like, oh, but no, that wouldn't be awesome, would it? No, because it's not really very square. Make it square. Be like, okay, up here I have 2 light bulbs. Okay, 2 light bulbs. By the way, are those light bulbs in series or are they in parallel? They are one right after another. They're in the same pathway. They are in series. So if you have one broken light bulb, the other one will not work. Okay, and then down here we have a switch. It looks like those light bulbs are on. And if the light bulbs are on, that switch must be open or closed. It must be closed. Okay, and then we've got our negative, positive, negative, positive, negative, positive. We got 3 cells that make up that battery of cells. Okay, and that's what it should look like. Okay, our next one here. Oh my gosh, what have we done? What's up with these batteries here? Those batteries are not connected in series because you'll notice when they're connected in series, the positive terminal touches the negative terminal. They're connected. The positive terminal is connected to the negative terminal. But down here, positive is actually connected to positive. Oh, and there are so many exciting things that I can't teach you about that because this is our freaking last lesson. It makes me so sad, but that's all right. You will survive. You will take physics, and then you will learn all this wonderful stuff. Okay. So let's draw this. So I have my positive here and my negative here. So I'm going to start with my battery. So I've got a positive terminal and a negative terminal. And over here, I have a positive terminal and a negative terminal. Okay. Do you see how I've now drawn this part over on the left? And now, boom, boom, boom. I'm going to draw my switch on the side because it looks busy on the bottom already. Okay, my light bulb is on, so my switch is closed. There we go. Okay. What if you wanted to draw your switch on the bottom? Could you do that? Sure. What do I care? Doesn't matter. Pick one. Okay? Pick. You can put your switch here. You can put your switch there. Really doesn't matter. Okay, let's try this one. I love it. Sometimes people try and make it square. They're like, I'm going to make it square. Okay, I got my light bulb. I got my switch. Let's pretend this one is off. Let's just pretend it's off. I know it looks like it's on. Let's pretend it's off because I want to draw an off circuit switch, I mean. Okay. La 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 la. This looks like a positive terminal here, so I've got negative terminal over here. So that's negative, positive, negative, positive, negative, positive. And then I've got a resistor, and this is what I'll see people do sometimes. They'll be like, oh, okay, I've got my resistor, and then I've got my light bulb. And I'll be like, why did you not make it square? Why did you not make it square? Because really, this wire here, could be any shape you want it to be, because it's a wiggly wire. We draw them square because it makes our lives easier. So let's draw that again. Let's go here, and I'm going to have my resistor. Chook, 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 chook. Boo. Oops. Tuk, 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 tuk. There. Boom, boom, boom. Boom. I might even have put the resistor over here, because that would have made it a little bit, less messy. Okay, but now I have a square. Oh my gosh, fantastic. The only time you're going to end up with things sticking off of your square is perhaps if you have something in parallel. Parallel is going to make it something less than a perfect square sometimes. Okay, let's try this one. Ooh, what is that? That looks like an LED. LED. Oh, I got a positive, negative, so I've got positive, negative, so I got negative, positive, and another cell, negative, positive. Here I come. I got my LED, which remember looks like a triangle, and it points at a line, and off of that comes some light. So little arrows coming off. Do you need to memorize that? No, go back and look it up. You got a whole sheet full of them. And then, just because I could, this one looked super fun. I don't know, that's like a shoulder of somebody who was in the diagram. Okay, okay. I've got the bumpy end here, so that's my positive terminal, that's my negative. So I have a battery of 4 cells. Okay, positive, negative, positive, negative, positive, negative, positive, negative, 4. Whew. I have a switch. Don't do this. Switch. No, 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 no. Don't do that. Square it off. Do I care that the switch looks like it's going this way? And I'm going to draw it going this way? No, I don't, because as long as it's attached to the negative terminal, it doesn't matter which direction I draw the lines. Okay, so there's my switch. And then I have a lamp. Okay. And then I have another lamp. So this is lamp M. And then I have lamp L. And then lamp L just goes right back to the batteries. And notice that, how is this resistor connected to this lamp? Is it connected in series or is it connected in parallel? It is connected in parallel. So we're going to have a branch coming off here where we have a resistor. Boom. How pretty is that? Okay. Did I do any others? Oh, I did a couple more because we need to talk about measuring the voltage gain or the voltage drop. So we are measuring voltage. And remember, voltage is the potential energy per amount of charge. So it is the joules per coulomb, which is, of course, a volt. And we are measuring the potential energy difference. Okay, it is the difference in potential energy from one point in a circuit to the other. So if I was measuring, if this is a 1.5 volt battery, I could connect my voltmeter here, okay? And the symbol for voltmeter is a V, so I'm just going to draw it like this over here. I could attach it here and attach it here. And essentially what I'm doing is I'm sampling the electrons at point A, and I'm saying those have a really high potential. They have 1.5 volts, joules for every coulomb, okay? And then I sample it over here, and I say, oh, those have 0 joules left for every coulomb. They're at a really low potential. And so the difference between 1.5 and 0 is 1.5. Okay? Now, that's not how this is set up. It's set up so we have our voltmeter. It's actually a multimeter. You could use it to measure volts. You could use it to measure amps. We're going to say volts. Because these electrons have 1.5 volts of energy per coulomb, they're going to start here with 1.5 volts, and they're going to finish over here. They have to drop all their energy. Okay, they drop all their energy over that light bulb. Okay, so this is also going to be 1.5 volts. And then you can think it's just like they've dropped all their energy, but they just skate on home, okay, to the 0. All right, so you give them 1.5 volts, and then they drop 1.5 volts over that lamp. So many more exciting things I could teach you, but no time. Okay. Now, when you're measuring current, you don't want to have the current, like, you don't want to have your ammeter in a separate branch, okay? Because then you'd be measuring how much current flows through this branch. And if you want to know how much current is flowing through the light bulb, you need to have the ammeter in the same pathway as the light bulb, because the current's going to flow at the same speed the whole way around. The electrons in one point cannot flow faster than the electrons in front of them. It's not like you have electrons flowing at different speeds all through the thing. If this were like bumper to bumper traffic, you can imagine if every car was bumper to bumper around the whole thing and everybody just moved, they would all have to move at the same pace. If anyone went faster, it would just bump the car in front of them and they wouldn't be able to move ahead. Okay? So an ammeter has to be connected in series with the circuit. And the symbol for ammeter is simply an A in a circle. So voltmeter was a V in a circle, and an ammeter is an A in a circle. Let's draw these circuit diagrams. Oh, by the way, my electrons are moving this way, so why the heck are my arrows going the other way? This is my electron flow. What are these yellow arrows showing? They are showing conventional current. Okay, here we go. All right, let's draw this puppy. Circuit diagram. I have my positive terminal on the top, my negative terminal on the bottom. I have a light bulb here. I'm going to show you 2 ways to draw this. You can either draw your voltmeter like this. Okay. Or, ooh, this is going to be fun. Watch this. does it matter if my branching point is indented or if my branching point just happens there? No, it doesn't matter. So either of these is acceptable, okay? Neither is incorrect, okay? The voltmeter is in parallel with the light bulb. Now down here we have an ammeter. Oh, we've got, let's see, my positive terminal, that's positive, is attached to my light bulb. So there's my positive terminal. It's attached to my light bulb. And then I have an ammeter. And that's it. So that's the last of my examples, and you guys are going to practice drawing some circuit diagrams. Think about the terms series and parallel as you go through here. I might just add in a few things like, is this a series circuit? Is this a parallel circuit? I haven't done it. You know what? Add it for yourself. Is this a simple series or parallel? Ooh, parallel circuit. See, you don't have to write the word parallel anymore. You can just draw it like that. Okay. Anyway, have fun doing this. It's the last thing that I'm doing with you, and I'm really sad because I won't see a lot of you again for another year. And if you go and you take Chem 11 Enriched, you'll be with Ms. Wu. If you take it the following year, if you're going to be with me next year, that's very exciting. And I'm just babbling now at this point because I haven't really eaten lunch. I've had about 7 blueberries. So I'm going to go have lunch. You do this worksheet, finish it up. It's due Sunday. Thank you for being such awesome students. I really have enjoyed teaching you. And have a great summer. Be safe. A great summer. Be safe. Bye.